information addition, the data that we want to store in those objects are represented as key value pairs. And they have their own life cycle simply because we create objects independent of the pod that actually consumes this information. Now, a config map is suitable for configuring applications with key value pairs in plain text representation. For example, if we want to provide connection URLs to external systems or runtime flags that will be evaluated by the application code. If we compare this with secrets, secrets are effectively a representation of sensitive data like passwords, API keys, SSL certificates. But keep in mind, the values that we assign to secrets are not encrypted. At any given point of time, they are just base 64 encoded. So if you know how to decode the value of a secret, you can easily retrieve the plain text value. One more side note, the config map and secret objects are stored in etcd, and they will be stored in unencrypted form by default. Now this is configurable and you can change it at any given point of time as the administrator to the Kubernetes cluster. Let's also talk about the consumption side of things. So once we created an object for config map or secret, we can consume it from a container. And in this case, we can consume it either as environment variables. That's a good option if the key value pair is relatively short and can be used from the application code to trigger how the runtime behavior should look like. And then we have the option to also consume a config map and a secret as a volume. That's a good option if the value assigned to a config map key value pair is something more structured. Let's say we wanted to define a XML, JSON, or YAML file. And we want to consume that content from the application code. Let's have a look at how to create a config map object with the imperative approach and the declarative approach, and then how to consume it from within a pod as environment variables or as a volume. So what you can see here on screen is the imperative approach. We can use the create config map command. We have to provide a name for the object. In this case, it's called dbconfig. And then we have to provide one or many of those options. The first option here from literal will define the plain text key value pairs on the command line. Then we have the option to point it to a environment variable file. The contents of this file usually assign key value pairs, each of which are specified on a single line and separated by an equal sign. Then we can define a config map by pointing it to a file as the source. And in this case, the file name would be used as the key name, and the content of the file would be used as the actual value. And if you wanted to parse a directory and use any of the files inside of it, you have the option to point it to a directory as well. Just wanted to show you some examples for those options in a table. And you can see here the last column spells out example values. So just to give you one example for for each of those options. Now let's actually have a look at something slightly more complex. In this command, we actually want to parse multiple key value pairs. And we're using the option from literal to provide the information. You can actually see we're using the typical naming conventions here for environment variables for the key db host, db user. That basically indicates to us we want to consume them as environment variables inside of the running container. If we want to represent the config map object in the form of a YAML manifest, looks pretty straightforward. You will actually see that the config map kind does not use the spec section. Instead, it will use the data section. And underneath there, we'll simply define those key value pairs. Now, if we wanted to consume the data from the config map as environment variables inside of the pod, it's actually relatively straightforward. You will simply just have to add a couple of attributes to the container. And you can see it's almost human readable. We can say env from, so environment variables from, a reference to a config map with the name dbconfig. As a result, once we started the pod object, we can shell into the container and inspect the underlying environment variables. Keep in mind, there's actually nothing inside of the config map definition that will enforce the naming conventions that we usually use for environment variables. That would be all uppercase letters and underscores to separate words. And yeah, that's really not something that Kubernetes handles internally. So if we were to define keys that don't follow those environment variable conventions, and we wanted to turn this into something that looks like environment variables, we can still remap the key for individual entries in a config map. I just wanted to show you one example here. Let's say within the config map object, we used lowercase database underscore URL, but we wanted to map it to a different name just to make it look like an environment variable. Then we can definitely achieve that with the notation that you see here on screen. Also wanted to show you one example for pointing a config map to a file as the source for its data. For that purpose, we can use the from file command line flag. And what will happen is that we will use the name of the file as the key and the content as the data represented by the value. So you can see in this case, we are actually dealing with a JSON file. So typical notation here, curly braces, key value pairs, and so on. You can see if we wanted to look at the config map in the YAML manifest representation, we would see the file name as the key, and then a separator character, and then the actual contents of the file underneath. Now, using such a JSON file is a good candidate for mounting this information as a volume. We already learned how to mount volumes, pretty straightforward, but we have to define a very specific type for that volume. In this case, the type is a config map. All we need to spell out here is the name of the config map, and then again, as usual, provide a mount path. Once we start up the pod, we would be able to shell into it and then inspect the mounted file that we wanted to parse. I want to mention a couple of information about what will happen if we actually change the data inside of the config map object. There's nothing built into Kubernetes that will automatically refresh the changed key value pairs in the pod that actually mounted or consumes the config map data. So if you wanted to automatically reload the information from a already running pod, then you will have to implement that as part of your application code. So for example, you could decide to reload the configuration data periodically or even on demand, for example, if you were to hit a specific endpoint. In this example, we will want to create a config map object from an existing YAML file. And for that purpose, we'll create a config map with the imperative command. Before we do so, let's have a look at the application.yaml manifest file. That is the one that we want to use as the source for defining key value pairs inside of the config map. So let's go ahead and create the config map with the imperative command. We'll say create config map. And the name of the config map is going to be app config. And as the pointer to the file, we'll use the command line flag from file, and we'll point it to application.yaml. All right, so we created the config map. Let's see if we can find it. We should see our config map, the object we just created. Let's also describe it, and let's have a look at it in more detail. So config map, and then the name is app config. And you can see here that we get the full contents of the file as the key value pairs. The actual key is the name of the file, and then the contents of the file are shown below. You could also get the same contents in the form of YAML if you wanted to. All we need to do is to change the command a little bit. So instead of using the get command, instead of using the describe command, we'll use the get command. And make sure that you print out the YAML representation of it. And you can see here under the data section, we have the name of the file and then the contents of the file. All right, so let's go ahead and create a pod that should mount this config map as a volume. So we'll start with the pod.yaml manifest file. As a starting point. I'll define that underneath the specifications. section. So we'll clean this up a little bit. And you can see as the actual type of the volume, we will use the config map attribute type. And here the name of my config map was app-config. And then lastly, we also need to define a volume mount. We'll define that for the corresponding container. And we want to mount this specifically under Etsy. Config. Right, I think that looks pretty good. Let's go ahead and create the object pod.yaml. All right, pod has been created. Let's see if we can get it into the running status. Go ahead and create the object. Pod .yaml. All right, pod has been created. Let's see if we can get it into the running status. And you can see it transitioned into running, means we can actually shell into it. So we'll open an interactive shell to the backend pod. And the shell that we want to open is the bin.sh. Let's see what I did here. kexec. I think we have to turn this around. -it. This is not called backup, that's called backend. All right, and now we should be able to actually go to the corresponding directory at the config. And inside of here, we should find our application.yaml file. Let's have a look at the contents of the file just to make sure that it looks as the source that we used when creating the config map object. As you can see, the whole structure has been preserved. So just to summarize, if we wanted to represent a structured file in any kind of form, say a XML file, YAML file, or something else that looks similar like that, and want to consume it from the running process or application inside of the container, you can easily represent that with a config map. We'll source it from the YAML manifest in this case, and then simply read it from the application logic. Let's have a look at the creation of a secret object with the imperative approach and the declarative approach, and how base64 encoding comes into play. in comparison to a config map. So let's first have a look at the imperative command. You can see that we can use the create secret command. Then we need to provide an additional option here, for example, generic, Docker registry, and TLS. Then we'll spell out the name and then the corresponding command line options that we've already seen for config maps. Those are exactly the same ones that we can use for creating secrets as well. Now, I just wanted to give you a high-level overview on these different options that we need to provide for a secret. The generic option creates a secret from a file, directory, or a literal value. That is very much similar to what we've seen for the config map. Internally, you will actually find that a secret will assign a specific type. In this case, the type is called opaque. If you wanted to derive secret data from a Docker registry, we can achieve that with the Docker registry option. Internally, the type here is kubernetes.io/docker config. And then lastly, if we want to represent a TLS secret, then we would use the option TLS. Now, as you can see here on screen, the command line flags for the generic option are exactly the same as they are for config maps. We can simply spell out key value pairs in plain text. We can point to environment variable files and individual files in directories. Now, there are also specialized secret types that I want to mention here. You can set them specifically with the command line flag --type. And that in turn will set the type attribute inside of the YAML manifest representation. In this table, you'll see some of those options. For example, if we wanted to represent a secret object that stores basic authentication information, that is username and password, then we can explicitly represent that with that dedicated type. In this case, kubernetes.io/basic authentication. Now you can see in this command, I put it all together. This will create a secret object of option generic. And we're providing key value pairs in plain text with the command line flag from literal. It pretty much looks exactly how we would create a config map. But keep in mind, the imperative command will automatically recreate the value in base64 encoded form. And we'll use it internally if you were to look at the representation of the object. Now we can also define a YAML manifest of a secret, but keep in mind, if you use this approach, you will have to represent the value in already base64 encoded form. And the way we can do that is with the help of the base64 command line tool. You can see here for the string that we provide, secret, we want to turn it into a base64 encoded form. We'll take that value, assign it as the value of the key value pair inside of the secret option, and then create the object from it. Now we can consume secrets as environment variables, and that looks actually fairly similar to what we've seen for config maps. So again, env from, so environment variables from, a reference to a secret with the name mySecret. It's important to understand if you were to shell into the running container that consumed the secret, the underlying value will be base64 decoded. So there's nothing that you actually have to implement in your code that will use a base64 encoding or decoding function. Now we can also parse a specific file here, let's say a SSH private key, and then use that for the purpose of providing a specific type. The specific type would be kubernetes.io/SSH authentication. And then if we wanted to use this file or the representation of it in the form of a secret, that would be a good use case for mounting it as a volume. You can see we have to spell out the volume type. In this case, the volume type is called secret. We provide the secret name, which is simply just the name of the secret object. And then we'll spell out the mount path, which we'll then be able to use from our application to read that file. Now, instead of using the data attribute inside of our secret object YAML representation, we can also use the string data representation. That's a convenience attribute for defining plain text values. So if you don't want to base64 encode those values yourself, then simply use string data instead. And this doesn't just apply to basic authentication as the type, it applies to any kind of type that we want to use. Once we create the object from the YAML manifest, the live object representation will basically use the base64 encoded form. And just one more comment about secrets. Secrets are not really secret in that sense. They are not encrypted data. They only represent sensitive information that we want to use inside of our pods. If you wanted to make it more secure, you definitely can. One way is to define RBAC permissions that will only allow specific users of your Kubernetes cluster to actually read from those secrets or manage them. The other option is to involve Kubernetes external secret services that can store sensitive data in encrypted form. Just wanted to mention a couple of examples here. HashiCorp Vault or AWS Secret Managers are options. They can be integrated in the form of an operator that is open source that we can install as a component in our Kubernetes cluster. And the way we can do that is with the external secrets operator. So have a look at that if that is something you will want to achieve. Here we are going to have a look at the creation of a secret object, and we will want to create the secret object with the imperative command by providing key value pairs on the command line. So let's go ahead and use the imperative command, which would be create a secret. We'll have to provide a specific type of secret, in this case the generic option. We'll call this DB credentials. And then use the from literal command line flag to actually spell out individual key value pairs. You may as well define multiple of those if you need them. For now, we'll just use a single one. All right, it has been created. Let's have a look at the object here and see how the runtime representation looks like. You will actually find that the imperative command will automatically turn the provided value of the key value pair into a base64 encoded format. You can see here under data, we still have the key in place, but the actual value has been base64 encoded. So now let's actually use the secret inside of a pod. We'll simply create a skeleton with the dry run command. And let's further modify that. What we want to do is to mount the secret as key value pairs. But one more thing that you may have noticed is that we are not conforming to the typical naming conventions of environment variables. So we can definitely change that. We can rename the key that we stored in the secret. Let's see if I can find the corresponding documentation for it. If I open this up here, we should find one example with secret key ref. Let's see if it gives us a full example here. Maybe I don't have it in this specific example, in this page I meant. So it looks like it's in a corresponding page. And what we can do here is to copy paste this portion so we can further modify our definition of the container. And that is what we're going to do. I'm going to use this as a starting point. and then further modify a couple of things. So as the actual key that we want to mount, we want to say this should be the database password of the secret called DB credentials. And then instead of using DB password in all lowercase, we'll actually turn this into a typical representation of a environment variable. This is of course optional, but I think it looks nicer. And if you were to look at the list of environment variables, it will clearly show you that we're actually talking about that kind of information. So we'll save that and we'll create the object from the pod definition. All right, it has been created. Let's make sure that it runs before we step into it. We'll want to shell into it as well. And now if you run the env command, we should find our DB password somewhere in here. You can see that the key has been turned into the typical notation for environment variables, and it was made available to any application that wants to read from it. What do we have to understand about config maps and secrets for the exam? So first of all, understand the purpose for a config map in comparison to a secret. So a config map basically just stores plain text key value pairs. They're a fairly good fit for simple strings like connection URLs, theme names, or anything that you will want to read from your application code in the form of an environment variable to effectively configure your application. Alternatively, you can definitely also read more structured data. For example, YAML manifests that you will want to read from application code. In comparison to config maps, secrets are meant for representing sensitive information. Keep in mind they are not encrypted and therefore not secret in that sense. They are only base64 encoded. So what I would practice in preparation for the exam is how to define those config map and secret objects with the imperative command as well as the declarative command. Know how to interact with those objects, and then understand how they can be consumed by pods as environment variables or as volumes. In this section, we are going to talk about the
In this video, we are going to explore how we can create high-level architectural diagram using MCP server capabilities of draw.io and xkelly draw. And to interact with these MCP servers, we are going to use Claude Desktop and Visual Studio Code. So let's get started with that. So first thing, I'm just going to open my Claude Desktop. So once you open your Claude Desktop, you need to go to in your settings. So I'm just going to go to File, and then I'm just going to application. It should include a React front-end, fast repair back, details around it. What you can do if you want to edit you can also open this one in xkelly draw web page, or you can also edit it over here. So if I just click on edit, then you can see like this particular window has been opened, and I can also just click on any of the part and can edit it, or I can just directly open it in the web browser of xkelly draw. And it's asking my permission. I'm just going to say open link. So from here also actually you can edit your image. So we cannot pass this remote MCP server in any kind of notepad. One is a web version, and it has created a payment kind of diagram like this. Here also actually it's a edit options, because this is going to be the remote server. So I'm just going to select this HTTP, and it's saying like URL of the MCP server. So here I can just say this is going to be the URL, and I can just pass it over here. And then it's saying enter server ID. I'm just going to say draw.io, and you can see like it has created a configuration like this. It's going to come up with 3 tools. I'm just going to start the server, and here we do have like one particular tool available. So let me just open GitHub Copilot chat and let's chat with this particular server. So I can just pass the same prompt, but instead of xkelly draw, I'm specifically asking to use draw.io. Now it's trying to create a diagram for us, and you can see like it has created it using draw.io MCP server. In this case, it's coming inline because it is rendering MCP app. And as mentioned over here, if you are using this particular remote MCP server, then the diagram is going to come inline in the AI chat interface only using MCP apps protocol. So same thing is being reflected over here. So here we are getting the diagram in the chat itself. We can zoom out or zoom in just to see a specific section, but it's not going to get opened on the web portal. It's going to be opened here only. Now the third option what we have is creating draw.io diagram using skills. So I'm just going to go to skills. I'm just going to click on this, and I'm just going to say upload skill, and I just need to pass an MD file over here. So to do that, I'm just going to go to this full documentation, which is here. From here, I will go to the parent one, and here we do have this skill.md file. So I'm just going to download it from here, and the same file I can upload it here. So this is a skill.md file, and this is going to be the custom skill which we are uploading. And now you can see I do have this draw.io diagram skill, and it has been listed in the my skill section, and it has been on by default. Now if I have to invoke that skill, then I can just say use draw.io skill to create high level payment design diagram. And it has started reading this draw.io skill, which we have just added it. And you can see like it has started creating the diagram in the XML format. So let's wait for this to be completed. And it has automatically routed us to the web URL where actually we can see and edit our diagram. And same thing it has listed here also, so with the details like what kind of layers have been included. So that's how actually you can interact with xkelly draw and draw.io using multiple options. That's all what we have in this video. Thank you for watching.
So GNOME is a good one. And yeah, my first one was Fedora, but note that that is a Linux distribution. It's not necessarily the desktop environment. Like, well, that's a good case in point. Like if you go to Fedora, you will get the opportunity to get multiple desktop environments. Okay, so here's the Fedora workstation. And then here they will say, well, you can also get Fedora KDE Plasma desktop. So Fedora workstation featuring the GNOME desktop. KDE features the KDE Plasma desktop. So KDE is its whole, like an whole ecosystem of all sorts of applications. And it is actually, often people will say that this is a good step for Windows users. And you can see why. It does the bar in this bottom. And look, it even mimics the Windows 10 kind of clock in the side here, the start menu. So this feels very familiar for people who come from Windows. KDE is often recommended there. So KDE is a good one to try.
Hey everyone, welcome back, and let's write some more neat code today. Let's look at a sliding window problem, a hard sliding window problem, sliding window maximum. The statement is pretty straightforward actually. So we're given an array of numbers, and we also are given a number k, which is going to represent the size of our sliding window. It starts at the very left and then works its way to the right. And so since it's size k, there's only going to be k numbers inside the window. And for each position that the window is in, we want to return the max value. So you can see that this is our input array, and our window is going to be size 3. So this is our first window, and the maximum value is 3. So then we see, and then we add a 3 to our output array. So the output is going to be an array. Next we see that this is the next position of the sliding window, and the maximum value in this case is still 3. So we put a 3 in our output. And the next position, we see that this is our window. The maximum value is 5. So we put a 5 in the output. Now, you might recognize one solution to this problem immediately. For each of these windows, why don't we just scan through the array, right? Like, it's pretty easy to find the maximum in an array, right? Like if we had 1, 2, 3, we just check every value and see, okay, this is the maximum. And then we just shift our window by 1 into the next position, right? And we keep doing that until we're done. Well, the time complexity of this is going to be roughly, since the size of our window is k, how many windows are we actually going to have? Let's say the entire input is length n. In that case, we're going to have roughly k times n minus k. That's how many windows we're going to have, right? And so this is going to be our time complexity. But I'm asking, is there a better solution? Can we actually make a linear time solution where n is the size of the input array? And the answer is yes. And I'm going to show you how to do that right now. So I'm going to show you the best solution, but one thing you have to notice first is this. So let's say this is our input array. We have 4 numbers and our window size is going to be 3, so k equals 3. Notice how these values are in increasing order, right? 1, 2, 3, 4. Okay, so we notice that. Now look at our first window. We have 1, 2, 3. We see that 2 is greater than 1. We see 3 is greater than 2. Now that's good. And so we scan through every element. 1's not the max, 2 is not the max, 3 is the max. So then in our output, for the first value, we're going to put a 3. Okay, that's great. Now we shift our window to the next position. So now I'm literally just going to repeat that process the brute force way. Now I'm going to check 2, okay. Now I'm going to check 3, 3 is greater. Now I'm going to check 4, 4 is the greatest. So we add 4 to our output. And so then we're done, we have our output, but we just did it the brute force way. But do you see the repeated work that we just did? As soon in our first window, we saw 1, 2, 3. We know 3 is greater. So we basically eliminate 2 and 3. And then when our window is at the next position, it's over here, right? 1 is no longer a part of our window, so we don't need to worry about 1. What about 2? Well, 2 is inside of our window, right? It's at the leftmost position. But since we know that this 3 is greater than the 2 anyway, why would we ever need to look at the 2 ever again? It's never going to be the maximum. And let me just make it even more obvious. Let's say our window size is 6 and this is our input array. Okay, so for our first window, we have to check, okay, the 1, another 1, another 1, another 1, another 1, and then a 4. So the 4 is our max. That's great, so we can save that. And then we shift our window to the next position and see we're repeating all that work over again, the 1, 1, 1. As soon as we see this 4, we know that these elements, as far as we're concerned, are useless to us. We never have to look at them again. They will never be the maximum inside of our window because our window is going to continue being shifted to the right position and the 4 is still going to be in the window even after these elements have been eliminated. And so the data structure we're going to use to eliminate these values is a DEQ or a DQ. And I'm going to show you the algorithm. And just to repeat myself, basically what I'm saying is if we have a window and we see a value that's greater than values that are previously in our window, then we can eliminate those values from our window. And so I'm going to show you the algorithm, and what you're going to notice is that the values in our DEQ are always going to be decreasing order. So this says decreasing. So we know our sliding window is initially size 6, right? K equals 6. So we're going to take the first 1, put it in our window, the second 1, put it in our window, and then just repeat that, right? We have 5 1s. We're going to add all of them. And then we get a 4. So since 4 is greater than the value at the top of our deck or at the rightmost position of our deck, what we're going to do is we're going to pop this value off. What we're going to do is pop the top of the deck, right? And now we're going to make the comparison again. We see there's still a 1, so 4 is still greater than the top of our deck. So we're going to pop this, we're going to pop that, we're going to pop all of them. And after that, we're going to add the new value 4. And so what are we going to add to the output? So we have an output array. What value are we going to add to it? Well, the leftmost value, and in this case, we only have one value, is going to be what we add to the output. So a 4. And so we're done with this comparison. We don't have to look at it again. And we don't even have to consider these elements anymore. And now we shift our window by 1 position. So we're introducing a new element, 5. So before we add the 5 to our deck, what do we have to do? We have to check, is 5 greater than the value at the top of our deck? It is, because the top value is a 4. So why would we ever consider the 4 as the maximum value ever again when we know there's a 5 right next to it? The answer is we don't have to, so we remove the 4 from our deck. And then we can add the 5 to the top, and then we know that there's only one value in our deck, and it's also the leftmost position. We are going to add that to our output, and now we're done. This is our output. But what's the time complexity of this algorithm? First, we took each one, added it to our deck, right? We did that for every single value. That was expensive. And then we also crossed out. We had to remove every single value from our deck. But adding and removing, we know adding and removing is an O of 1 operation to our deck. And we had to do that for every single value in here potentially. But that's still O of n, right? The result is O of n, which is why this is a really good solution. And I'm going to show you one last example. And by the way, this is called, the type of problem this is called a monotonically decreasing queue. And the reason is because our queue is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a queue rather than a stack is because we want to be able to add and remove elements from the beginning in O of 1 time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of 1 time, which is why we need a queue. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our queue. Then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add the 7. We only want to remove smaller elements if they exist. But in this case, that's not true. So we add the 7. And notice how these values are in decreasing order. We have 8 and then we have a 7, right? They're in decreasing order. So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first thing to notice is that the 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck. So we add it to the output. And lastly, we look at the last sliding window, which is these last 2 elements. And we know that the 7 is no longer in bounds, right? So from the leftmost position, which is this, we pop from our deck. We make one last comparison, right? We just added a 9. Let's take a look. Is 9 greater than the top value of our stack? Is it greater than 6? It is. What does that mean? That means we have to pop from the top of the stack, the rightmost position, or rather the queue. I don't know how many times I said stack, but we're going to pop from the rightmost position in our queue. And now we are allowed to take the 9 and append it to our queue. So we add the 9 now. We know that this is the leftmost position in our queue, and we know that in this window, 9 is the maximum. So we did this correctly, right? So we can take the 9, add it to our output. So this is the result that we're looking for. And I hope this demonstrates a few of, like, when you actually run through examples, it shows you like what you need to know. It shows you why we're using this data structure, and it shows you why it's so efficient. So now with that in mind, the coding solution is not too bad. So we are going to have an output array to put the values in. We're also, for our window, we're going to have some pointers, so left and right pointers. These are going to represent where our window currently is. They're both initially going to be set to 0. And we're also going to have a queue. In Python, we can do collections.deck. And so we're going to run this until our right pointer is no longer in bounds. So while right is still in bounds. So we want to our queue, we want to be able to append the value, this value, right, R. And instead of doing nums of R, I'm just going to do the index itself. So this is going to contain indices, because we know we can take an index like R and then easily find the number that it maps to by just taking nums of R, right? But before we're even allowed to append a value to our queue, we have to make sure that no smaller values exist in our queue. So while the queue is non-empty and the top value in our queue, or the rightmost value in our queue, is less than the value that we're inserting, nums of R, which is the current index we're at. So while smaller values exist in our queue, we just want to pop from the queue, just remove values while that condition holds. And only after we do that are we allowed to add the new value to the queue. We also, if the left value is out of bounds, then remove the left value from the window. So if our left index, left, is currently greater than the leftmost value in our queue, then we can pop from the left of the queue. So basically, we know left and right represent our window. So if our window is if this value, the leftmost value in our queue, is out of bounds of our window, we're going to remove that. We have to remove that. And this part is kind of an edge case. Since we are starting at our window being left and right both being at 0, we have to check that our right plus our window is at least size k. So if we want to update the output, we have to make sure our window is at least size k. So that's basically what I'm doing here. And for each iteration of the loop, basically for each window, we want to append our output with the maximum. So we know the maximum is the leftmost position in our queue. And we want not the index, but we want the actual value itself. Don't forget, like me, to update your pointers. So we know right is always going to be incremented. So at the end of our loop, we can increment right. Left, though, is only going to be incremented once our window is at least size k. So we're going to put that inside of this condition. And now the only thing left for us to do is return that output. And it works. And we know that this is the most efficient solution
Back in 2006, AWS didn't really exist. Amazon just needed a way to keep their bookstore from melting under its own weight. So they built a storage service. They called it S3, sold it as a service to anyone else, and the rest is history. A year in, it had 10 billion items. Today, we're looking at over 500 trillion. That is half a quadrillion objects. It's a number so big it feels fake. And look, S3 is a masterpiece. The APIs, the features, the way it just works. But for the most of us, S3 has three massive catches. First, the cost. It's not the storage that gets you, it's the egress trap. You pay a fee for fetching your stored objects, often more than just storing them. Second, the complexity. To actually save money, you basically need a PhD in AWS pricing to navigate Glacier, intelligent tiering, and API request fees. And lastly, control. For a long time, the answer was Minio. It was the gold standard for self-hosting and Kubernetes object storage. But lately, things have changed. Between the licensing shift, the gutting of community features, and the sudden change to maintenance mode, Minio has started to feel less like a community tool and more like a giant that's getting old and corporate. Sound familiar, anyone? So what if we could have the full S3 compatibility, the CLIs, the APIs, the workflow, but in a package that's actually open source, like for real? Something that doesn't need a cluster of enterprise servers, but can run on a couple of old laptops or a Raspberry Pi you have lying around. That's where Garage comes in. It's not just an alternative, it's a different way of thinking about object storage. Let's get into it. Garage is open source, written in Rust, and as befitting as a self-hosting platform, it's served on Forjo, a self-hostable Git alternative. There's also a GitHub mirror for exposure, but beyond this, it has a fantastic documentation website with easy-to-follow tutorials and reference manuals. For context, the goal of Garage is a lightweight object store for self-hosting. It's meant to be resilient, simple, and handle extreme load. One of my favorite lines here is the feature extensiveness, which aims to cover the majority of S3. This is important for two main reasons. One, well, you can enjoy your own S3, that's obvious, but the second, if you're running S3 in production, but it makes sense to use another local S3 for staging or dev, maybe you're just starting out and have servers lying around and you can start using the same APIs, enjoy the same features with your local physical RUC. What are these amazing features I'm so excited about? Well, the S3 API to start with, but also allowing you to distribute different cluster nodes in different geolocations, just like S3. This already suggests a huge feature, which is clustering of nodes forming a scalable object storage. Like S3, it can serve static websites, and we'll see that in action, and even an integration to orchestrators like Kubernetes and Nomad. Now, I thought I'd be able to pre-install it, but not only I'm not sure what the Garage in Homebrew is for, it's not officially documented on their website. The release builds don't offer a Darwin option for my Mac, so I went with the containerized option. We can run it, but it'll immediately fail asking for a configuration file. So let's create our first Garage TOML, starting with a few paths for data and metadata, the engine, which is my beloved SQLite, a replication factor, which we're not going to have, and a bunch of other options for the API, web hosting, etc. Do note, we've provided a few secrets here for communication encryption. Well, didn't really provide it yet, so let's create the key first and add it to the RPC secret, metrics token, and the admin token. Yes, I'm a genius that uses the same key for everything. Sue me. A quick doc run and we're up. One thing that's missing, which sharp viewers have probably already noticed, is multiple ports serving the K2V API, S3 API, admin APIs, and the web server, all of which we didn't actually wire through Docker. So if you're running a containerized version of Garage, map these out and we're good to go. Browsing the first port sends back familiar access denied XML, which for anyone who had ever had the pleasure of working with S3, this is not the first time seeing one of these. There's a 404 not found from our web serving port. Now everything we're going to run is being done via the Garage CLI. Since we're working through a container, we'll exec to the container followed by Garage CLI and command and then its attributes, like the help menu,